everyone. This is the third lecture of this week. Today we will continue discussing solution of boundary value problems, but today's topic is Airy's stress function. You see, what we have done so far is we have derived the equations for plane strain and plane stress problems, governing equations, and those equations are written in terms of stresses, and also the governing equations are written in terms of displacements. Okay, we are we are in the verge of solving those equations, applying those equations for solution of different boundary value problems. Now, if you recall, there are many solution techniques available. They can be, every methods have their own advantages and limitations. We won't discuss that in detail in this course. Instead, what we do is we will try to understand two methods. One is power series method, and then towards the end of this course we will spend some time on complex variable method. Okay. We'll be having very brief discussion on numerical methods, what are the available numerical techniques towards the end of this course. Then most of the time we will be spending on power series method and then complex variable method. Okay. Now, let us first let us have a quick review of where do we stand right now. Now, you see, these are the equilibrium equations for plane strain and plane stress problem. Equilibrium equations remain same, and then we have the compatibility equation, strain compatibility equation, and again for plane strain and plane stress problem, the strain compatibility equation remains same. Now, when we write the compatibility equation in terms of stresses, then the plane strain and plane stress becomes like this, okay, where B is the Bx and By are the body forces. Now, if it is the body force is 0 or body force is constant, then what happens? This part becomes 0 and this part becomes, the entire part becomes 0, and the equation becomes this is equal to 0 and this equation is equal to 0. So, for plane stress and plane strain problem, if there is no body force and or the constant body force, then again this equation is also same. Now, next, so these are the equations that we have already discussed in previous classes, derivation of these equations and the assumption which constitute the basis of that derivations. Okay. Let us now define one potential called body force potential, and which is defined as like this. Suppose if V is the body force potential, then if we differentiate V with respect to any coordinate axis, gives the body force in that direction. So, if we differentiate Y, it gives me By. What we do here now is, let us not bother about what is that potential and how to get that potential for different kinds of body forces. Whenever we come across that, whenever we apply these all the techniques that we are going to learn to solve some problems, and in that problem whenever we encounter any body force, then we will come to this point, what is that potential, and depending on the body force and the direction, how to construct that potential. Suppose we have the potential V, which is body force potential, and derivative of that potential gives us the body forces in respective direction. Now, if it is, then if we substitute, now this is the equilibrium equation, if you recall. Now, if we substitute this body force potential into this equation, this potential into this equation, then what we have is, finally we have an equation like this. Okay. Now, what we have is, if we do it, then the first term becomes this thing, if we use different color. So, if we substitute Bx in this equation, then we have del x, the first equation, that becomes sigma x minus V plus del sigma x y by del y, that is equal to 0. 0 means we has, okay, and then del sigma x y del y plus del y sigma y minus v, that is equal to 0. So, if we apply the body force potential into the equilibrium equation, we have this. Please correct, these are all sigma xx, this is sigma yy and so on. That is how we represented stress components. Okay. Now, once we have that, then this is the your equations that we have. Now, let us introduce another important term, which is Airy's stress function. You see here, these equations, the governing equations are written in terms of stresses. Okay, this is the equilibrium equation, then we have the compatibility equation as well. Now, if we have to directly solve it, then what are the how many unknowns we have? The unknowns are 3 unknown in plane stress and plane strain. In plane problems, we have sigma xx and then sigma xy and then sigma y. This should be sigma. This should be sigma xy. Okay. Now, let us define a potential, potential phi, such that the how to, whether that potential exists or not for a given problem, how to construct that potential, we will see that. Suppose, say phi is a potential which is defined as sigma xx is equal to del 2 phi del y2 plus v, and then sigma yy is equal to del 2 phi del x2 plus v, and then sigma xy is equal to minus del 2 phi del x del y. Now, you see, if I define a potential phi and its relation with stress component sigma xx, sigma yy and sigma xs, you check that this phi, if that phi exists, if we substitute in this equation, phi automatically satisfy this governing equation. You can try this exercise. Now, what we have done is, say phi is a potential which is related to stresses, different component of stresses. This, if we have some phi, then that phi automatically satisfy the equilibrium equation. If you substitute sigma xx, sigma y1, sigma xy from this into this equation, you will see that equilibrium equations are satisfied. Now, if we have some phi, equilibrium equations are satisfied. Now, in addition to that, if we make that phi satisfy the compatibility equation, then we can say that phi carries the information about the solution of this equation. You see, governing equations are two, one is equilibrium equation and the second one is compatibility equation. By choosing phi like this, governing equations are already satisfied. Now, next job, if we can show, if we can make this phi, if we can find out a condition such that the phi can satisfy, if that condition is met, that phi also satisfy the compatibility equation, then we can easily say that phi satisfy both the conditions, compatibility and equilibrium equation, and therefore, phi carries the information about the solution of these governing equations. Okay. Now, to make it clear, suppose if you recall, these are the governing equations. This is the governing equation for plane strain and this is the governing equation for plane stress problem. Okay. Now, we have the phi is the stress potential. It is called stress potential because it is related to stresses, and the sigma xx, sigma yy and sigma xy are related to phi as this. And we have already checked, we have not done that exercise here, but you can do that. We have already checked that or discussed that this definition of phi, this relation of phi satisfies the equilibrium equation. Now, here we have the compatibility equation written in terms of stresses. What next we do is, we substitute these sigma xs and sigma yy and sigma xxy in this equation and find out that what condition phi needs to be satisfied such that the equilibrium conditions are satisfied. Let us do that exercise. So, now if we take the first term in this equation, if we take the first term in this equation, which is same for plane strain and plane stress problem, then what we have is this. Now, if you recall, del 2 is what? Del 2 is the now del 2 is, if you recall, del 2 is del 2 del x 2 in 2 dimension plus del 2 del y 2. So, what it becomes is del 2 del x 2 plus del 2 del y 2. I could have kept it del 2 as well, but let us write it in detail. And then we have sigma x is this, sigma y is this. Then we have del 2 phi del x del y 2 plus del 2 phi del x 2 and then plus 2 v. This is the first term, right? And this becomes what? This becomes that del 2 del x 2 plus del 2 del y 2 of again del 2 del x 2 plus del 2, you can check it, del y 2 phi plus del 2 del x 2 plus del 2 del y 2 of v. So, this is essentially del 2 and then this is again del 2 of phi and plus there will be 2 here, there will be 2 v. So, this becomes 2 del 2 v. Okay. So, now, so this is the first term. Okay. Similarly, if I substitute these expression, this expression for velocity potential means b, what is the expression for by and what is the expression for bx. If we recall that bx was minus del v del x and by was minus del v del y. If we substitute that into this equation, into right hand side of this equation and then do the manipulation, then what we have finally, we have this is the equation, we have finally this. What is this term? This term was, if you recall, this term is essentially the entire term is del 2 which was del 2 del x 2 plus del 2 del y 2 square or del 2 del x 2 plus del 2 del y 2. Okay. And then this is the right hand side. That exercise we have not done here, but you can do that, okay, the same way. So, in both the cases, plane strain and plane strain problem, the left hand side remains same and then the right hand side is different depending on the plane stress and plane strain problem. Now, this entire thing which is del 2, this can be written as del 4 phi. This del 4 operator is this operator is del 4 operator. Okay. So, essentially then equation becomes, in terms of operator, if we have to write, essentially the equation become this, your del 4 phi is equal to this and del 4 phi is equal to this, and del 4 is called biharmonic operator. Okay. Now, again, if V is equal to, if there is no body force, then this term becomes 0, this term becomes 0 and this term becomes 0, and then essentially we are left with del 4 phi is equal to 0, whether it is plane stress or plane strain problem. In both the cases, this is equal to 0. This equation is called biharmonic equation. Now, this equation tells us a very important, very interesting story, and probably if you recall, it's in one of the classes we discussed that as well. You see, okay, before coming to that point, what we have done here is, what advantage we have here is, see, essentially we had 3 unknown, sigma xx, sigma yy and sigma xy, and the 3 equations, equilibrium equations, 2 and 1 compatibility equation. Now, if we have to solve these 3 equations, if we have to directly solve this equation, directly find out all the unknown, we had to solve 3 equations. Now, here what we did is, we combined 3 equations and now we have just one equation, and therefore, we have just one unknown. This unknown is phi, and how this phi is defined? This phi is defined in such a way, the relation between phi and the stresses are defined in such a way that equilibrium condition is automatically satisfied, and then del 4 phi is essentially what? Del 4 phi is essentially the compatibility condition, right? It is the if phi satisfies this equation, then the compatibility condition, compatibility condition is also satisfied. By construction, phi satisfies equilibrium condition. In addition to that, if phi satisfies this biharmonic equation, means compatibility condition is also satisfied, and phi is the solution. Phi carries the information about the solution of this problem. Now, for us now this phi is called Airy's stress function. Okay. Now, what we do is, instead of solving these equilibrium equations and compatibility equation, we solve this. Okay. We have just one unknown, but again there is no free lunch. If we have to reduce the number of unknown, we have done it, but at the cost of increasing the order of differential equation. Here you see, now we have to deal with fourth order differential equation, and we will see that how it can be, how it is to be solved. Now from onwards, our equations, governing equation is, this is our governing equation, del 4 phi is equal to 0 if the body force is 0, otherwise the governing equation would be this, and this equation will be subjected to some boundary conditions. We will solve this equation, find out phi. Once we have phi satisfy this equation and all the boundary conditions, then we know the relation between phi and stresses. From that relation we can determine the stresses. Once we have the stresses, we know the relation, constitutive relation, which is the relation between stress and strain. From that constitutive relation we can find out strains. Once we have strain, which is the derivative of displacement, by integrating strain we can have displacement, and then we have the complete solution of the problem. Okay. Now, here one important point you observed before also, when we solve this, right hand side is 0 irrespective of the plane stress and plane strain if the body force is 0, and another important point is the solution of this solution does not, the phi does not carry any information about the material property. It means that, and phi is directly measure of the stress field, it means that if there is no body force, in absence of body force, the distribution of stresses, they do not depend on the material property. But when from stress we get the strain, then the material constitutive property, constitutive relation will come into picture. It means that if we take two identical samples mean geometry and boundary conditions same, but one sample is prepared of steel and another one is say prepared of some other material, say aluminum or glass or wood. And if we apply, if both are having same boundary condition, same dimension and the same external loading, stress loading, or the traction boundary condition, then in both the cases the distribution of the stress field will remain same, whether it is steel, wood or any other material, the stress will remain same, and that is the important, that is a very important property that we use in photoelasticity, and the detail of that photoelasticity, how to exploit this equation in experimental in stress analysis, that we discussed towards the end of this one of the lecture towards the end of this course. Okay. Now, what we do is, once we have this, next is, this is next what we do is, once next class we start with this equation and then see how to solve this equation, what are the different techniques or that we already discussed, that we will be using power series method. We will take an example and demonstrate how these Airy's stress function can be used to solve the boundary value problems in elasticity. Okay. So, next class we will be demonstrating this through one example. See you in the next class. Thank you.